The notes in this section are like way too long for what they're supposed to be. But the deal is you're supposed to graph equations and you're not really supposed to know much about them. So kind of pretend you don't know a whole lot. Or maybe you don't because you forgot it all. I don't know. But you're supposed to do basic things like find x-intercepts and find y-intercepts and test for symmetry. Some of the simpler stuff. But we're not going to do all of these. Here's the first thing in your notes. Start with the following points are on the graph of the equation negative 3x plus y equals 6. If this was a multiple choice question, what would you do with the answers? You plug them in. All right, so let's just check this one, x, y. Right, that's an x, that's a y. A negative 3 times a negative 2 plus y, which is 0, is supposed to be 6. Is that true or false? That's true. So what do you know about that point? Negative 2, 0 exists on the graph. We're not going to do any more of those. I meant to delete these from your notes, but I did not. Because it doesn't help you do anything with SAR's graphing. All right, let's do the actual quadratic. And this is by plotting points, even though you could go to your TI-84 and type it in. But the whole deal here is just plot points. What we'll do is we'll find the x-intercepts first. How do you find an x-intercept? How do you find x-intercepts? Yes, you cross the x-axis. What do you know is true at the x-axis? Y equals what?
0.
So 0 equals 2x squared minus 4x plus 3. Figure out your zeros if they exist. They may not exist. How would you figure out your zeros if they exist? Oh, somebody knows. What do you want to do with that equation? Want to try to factor it? Try to factor it. You guys are wearing masks, so I cannot hear you. You saying simplify radical? Quadratic formula, yeah. It doesn't factor, does it? 4 plus or minus square root of a negative 4 squared minus 4 times 2 times 3. All sitting over twice a 2. Does it have any x-intercepts? I cannot be this much faster than y'all. Does it have any x-intercepts? Why not? Why not? It's an imaginary number. This is non-real. So no x-intercepts. Now you always go after that because sometimes it exists. If it does, it makes your life easier. Well, maybe we can find a y-intercept. You're always going to get one of the two. Sometimes you get both. How do you find a y-intercept? Let x be 0. Well, that's easy. You let your x be 0. What's your y-intercept? 3. Finally, I got a point on that graph. For all that work, I got a point on that graph. Remember what a quadratic looks like? Looks like a U. Now, you are expected to remember this. How do you find a vertex? There's a formula for it. How do you find the vertex of a quadratic? It's part of the quadratic formula. That little formula right there. X is opposite b over twice a. Opposite b over twice a. All right, so x would be opposite b. B is a negative 4, so opposite is a positive 4. Sitting over twice a 2. That's a 1 when everything's said and done, isn't it? All right. I'm going to make a table based on what we got here. We did something earlier. We found a y-intercept at 0, 3. We've got an x coordinate of the vertex at 1. Now, if I have x, how do I get y? Plug it in, and I'm not going to write that out for you, okay? But I'm taking this one and I'm going to throw it in that equation up top. So if I plug in a 1, I'll have 2 times a 1 squared, that's still 2. Minus something, 4 times 1 is 4, 2 minus 4 is negative 2. Add 3, I get 1 back. That's a point I can plot, 1, 1. Now, this point, the vertex, is very, very important. It's basically the middle of a graph. So we'd like to draw in what we call the axis of symmetry. You've got this little point pointing to the left of your vertex. Where's another point? To the right. So it's going to be over here. So we actually found another point. It was at 2, 3, and it was found by symmetry. When you're dealing with a quadratic, this is usually one of the things you do, and you don't always end up with a table that looks like this, but I want you to notice something. The other 2 points were exactly 1 unit left and 1 unit right of where? Vertex. So let's make that part of your notes. That's how you graph quadratics. It's a 3-point technique, and it always works. To graph a quadratic, find the vertex, then a point left and right of the vertex. Now, obviously, you should go after your x and y intercepts too if you can. You may have enough points if you get those, but you always want that vertex. Nothing else matters except that vertex. If you don't have that vertex, you're probably not going to graph it right. Your graph will look funny. I've done this for a while. And that's quadratic. Straight out algebra 2. One thing I did forget to do was draw my little U. Alright, so that's out of the way. Finding intercepts from a graph. Seems like a simple skill, but you put this on a test and kids miss it. Baffles me to this day. Find the intercepts of the graph. 2 types of intercepts. There's x-intercepts and y-intercepts. So let's go after our x-intercepts first. Emma, can you give me a pair of x-intercepts? 4.50 is one of them. Bryce, can you give me another pair? 0.3 is not an x-intercept, Bryce. 3/2, 0. Savannah, can you give me another one? -3, 0. Is that all our x-intercepts? All right, y-intercepts are up next. Allison, can you give me a pair of y-intercepts? 0, -4/3 is one. Leah, you got a pair? 0.3. And Lauren, last pair. So don't miss questions like that. Little things to note on the x-intercepts. What was y always? On the y-intercept, what was x always? Those are concepts. Those are understood concepts. Use them in your favor. All right, so here's where we actually get into this. Find the x-intercepts and y-intercepts of this graph and then graph by plotting points. Won't be too hard. Let's go after our x-intercepts first. How do we find an x-intercept? Let y be 0. So this one will be a lot easier than the last one we looked at. If 0 equals x squared minus 4. Does that factor? +2 minus 2. Where are your x-intercepts at? X-intercepts are at, I'm going to use ordered pairs here. -2, 0, and 2, 0. The y-intercept's probably not even worthy of showing work. I'm just going to let x squared be 0. So what's left if I let x squared be 0? -4. So it's at 0, -4. Now let's see what we got and see if it's actually enough to graph this thing. Is it? We may not have realized when we found it, but this little point right here, isn't it smack dab in the middle of two other points? What does it have to be? That happens to be the vertex. It happens to be. And I'll make a table and I'll show you too kind of how you might know if it's a vertex or not. So we actually did have enough to graph that thing. It did happen to be the vertex. Tables are kind of nice to do because they help you see patterns and stuff. I'm going to put this in the middle of my table because it happened to be the vertex. The two x values were exactly 2 units away. Good hint that you're a vertex. Good hint. Because of what happened to the y values. What's true about the y values? They match. It's matched. Look up at the table we made before. We had 2 points centered around a vertex. They both happen to be the same distance from the vertex, 1 and 1. But more importantly, what was true about the y values? They matched. When you see those y values matching, you know you got the vertex smack dab in the middle. So look out for that. Well, that was easy enough. Huh? It's Commandment 1 and Commandment 9. They work very well. I never had a kid until I was 38. You know, it works pretty good. And boys, it is your fault if she gets pregnant. Plain and simple. I'm sorry. We get to test symmetry. These are fun. The graph is said to be symmetric with respect to the x-axis if for every point xy on the graph, the point x negative y is also on the graph. Consider this, x minus 2 equals y squared. So I guess we're tasked with graphing this thing. That's not exactly a really fun thing to graph by hand, but we can do it. Find our x-intercept. How do we find an x-intercept? Plug in a 0 for y. X minus 2 is 0 squared, so it's at x equals 2. Find a y-intercept. How do you find a y-intercept? Let x be 0. So 0 minus 2 equals y squared. Well, this is going to be ugly. Y would be plus or minus root what? Root 2. Root of negative 2. That. So it's imaginary. Now, I don't guess you guys probably don't recognize what this thing is, but if you were to take the square root of both sides, you have a graph that looks like this. At least what the equation would look like. Plus or minus root of x minus 2. Now graphing these by hand, kind of interesting here. Give me a number you can take a square root of. 4. I agree with that. How could you make this radical of 4? What would x need to be for this radical to become a 4? X would have to be 6. 6 minus 2 is 4. Root of 4 is plus or minus 2. Give me something else you can take the square root of. How about 1? What would x have to be? 3. So 3 minus 2 is 1. The root of 1 here being plus or minus 1. That's actually enough points here. The easiest thing you can take the square root of is 0. That's where the 2 came from in the first place. Plus or minus 0. This is actually a sideways parabola. It looks like this. So this thing has symmetry with what? I read it to you. X-axis. Because for every positive xy that you have on the graph, what else do you have on the graph? We had a positive 1. What else do we have? Negative 1. We had a positive 2. We had a negative 2. And most of these are easy to visualize. The issue is sometimes you have to visualize them. But I think you can see there that you have symmetry with the x-axis, what you hot dog or flip over. And that's kind of a rule. Did they give us the function rule yet? No, not yet. So we'll talk about that later. If a graph is symmetric with respect to the x-axis and the point 3, 2 is on the graph, what other point is also on the graph? So it's saying I'm symmetrical with this guy. What other point has to exist? Not negative 3, 2. 3, negative 2. Because of distance. The distance there is 2, so the distance has to be repeated. You can also follow that function rule, which is over on the right. We're going to rewrite that a little bit differently. Now here's one with symmetric with respect to the y-axis, and I'm not going to bore you with making a table. If you remember your transformation rules, this goes to the right 3 and down 2. Maybe you do, maybe you don't. And from there, it's going to rise 1 and run 1. It's going to look like this. Now, I have no idea why that example is there. Does that thing have symmetry with the y-axis? Does it have y-axis symmetry? The y-axis is way over here. This is a horrible example. Should not even be there. So let me redo this one. Consider y equals x squared minus 2. That thing is just going to fall 2 units on the x-axis, on the y-axis. It's going to look like that. Does that have y-axis symmetry? Yes. And they do have some function rules, which we're going to rewrite in a little bit. They're coming up. But it's saying that for every positive xy, you happen to have this negative xy on the graph as well, because of distance concepts. So here's our easy example with a point. Consider a graph that has respect to the y-axis, symmetry of the y-axis, and the point 3, 2 is on it. What other point is on it? Yeah, this is Emily's answer from earlier. Got to maintain that distance of 3. I guess the last thing in your notes here before we move on to the harder part of this section is probably origin symmetry. Graph is said to be symmetric with respect to the origin if for every point positive xy on the graph, the point negative x, negative y is on the graph. And I want to add to this all graphs with origin symmetry are reflected on the line y equals x. They kind of give a hint on that on this example. But you'll see as we do these things. Wait a second. Negative x. Y equals negative x. So first we get to work with a nice little point. The graph is symmetric with respect to the origin. The point 3, 2 is on the graph. What other point is also on the graph? Yeah, if you look over at your rule, it says change signs on both. Negative 3, negative 2. So the last couple of slides just went over the ideas and the basic ideas of being symmetrical with certain things, the x-axis, the y-axis, or the origin. But now you actually need what's called the test for symmetry. First test for symmetry is the x-axis. And x-axis symmetry was right here. What changed signs? Y changed signs. You're not going to like the way this test for symmetry are written because they use function notation, which is kind of the bummer part of it. Test for x-axis symmetry says that f of x equals negative f of x. Kind of funny looking, isn't it? It means that if you plug an x value in, you should get 2 back. You should get back both a positive and a negative y value that are the same. That's what it means in words. But we're not even going to be plugging in numbers. I mean, we're literally going to do the tests, which makes it a little more difficult. Look back on your notes on y-axis symmetry. What changed signs? X, but did y stay the same? Okay. So its function rule is that f of x equals f of negative x. The y value stay the same. That's that function notation. Y of a positive x must be equal to y of a negative x. The last one's origin. I'm having a moment here. I'm trying to remember the rule. Pretty sure it's f of negative x equals negative f of x. I'm actually going to check your book on that to make sure I'm right. Sometimes I'm wrong. And this is one of those things that I never actually much cared for. Same thing I get on to y'all about whether you care or not, you need to learn it. It should be right. Then it actually give them a function rule. That's correct. Anyways, not the fun part of this section. Test this sucker for symmetry, following those function rules off to the side. This is x squared minus 9 over x squared plus 2, and we're supposed to check it for lots and lots of symmetry. And we'll do the x-axis test first. The x-axis test says f of x equals negative f of x. And we're literally going to do what it says. F of x is x squared minus 9 over x squared plus 2, isn't it? Isn't that what it is? It must be equal to negative f of x. What do you multiply this equation by? If f of x must equal negative f of x, what do you multiply this equation by? A negative. Now, when you multiply a number by a negative, what gets the negative? No. What, Haley? Either the top or bottom. You can't give it to both the numerator and denominator. That would change it. You only negate one piece of it. And if you give everything a negative, that means you're multiplying the top by a negative and the bottom by a negative. But you didn't change it at all, did you? You multiply everything in the top by a negative and everything in the bottom by a negative. Did you actually change it at all? No. You didn't change, you just made it positive again. So you just give the top that piece. That is the thing that gets kids, is working with fractions and negatives. It's only given to the top or the bottom. Now, is that true? Is what I wrote true? Is x squared minus 9 over x squared plus 2 equal to negative x squared plus 9 over x squared plus 2? No. They don't visually look the same, kids. The rule says they need to look visually the same. So, not true. There is no x-axis symmetry. Pretty sure I misspelled symmetry. Check it for y-axis symmetry. Well, y-axis symmetry is where we compare f of x to f of negative x. So x squared minus 9 over x squared plus 2 must equal, everywhere I see an x in f of negative x, what do I replace it with? Negative x. So the original equation here was x squared, a negative x squared minus 9 over a negative x squared plus 2. Will that thing look the same when everything is said and done? I'm seeing a couple of nods saying yes. Why is it going to look the same when everything is said and done? What happens when you square those negatives? They become positive. So what we see is that x squared minus 9 over x squared plus 2 is equal to x squared minus 9 over x squared plus 2. Without looking at the graph, we already know that this thing has y-axis symmetry. Because the two equations are identical to each other. And the last one is a check for origin. We've got f of negative x equal to negative f of x. Now, I'm going to save some time. Well, actually, I won't because there's people at home and I don't think kids ever really pay attention to what I'm saying. So that's what happens when I plug in that f of negative x. And then I'm going to distribute the negative. This would be the setup on this thing. When I'm done, I'll have x squared minus 9 over x squared plus 2 equal to negative x squared plus 9 over x squared plus 2. Do they match? So no origin symmetry. And I reckon we'll start here tomorrow. Go and enjoy your day.